Okay, so let's summarize this topic. So we saw that reinforcement learning must generalize, or we observed that it must generalize. Remember the Pac-Man demo. It must generalize on observed experience if it is to be applicable to real-world domains, right? Just because our state space is usually way too big. We can use parameterized function approximation to represent our knowledge about the domain or the state action values. And later on we'll also see how we can do this to approximate the policy, actually the actual policy that we're trying to converge on. Then we saw how to use stochastic gradient descent to update the tunable parameters such that the observed error that is based on TD learning or full rollouts in the Monte Carlo case is reduced over time. When using a linear approximator, specifically a linear approximator, the LSTD method can be used, and it provides the most sample efficient approximation. Sample efficient, just as a reminder, is an algorithm that does not require a lot of samples from the environment, right? So we say if it doesn't require a lot of samples, we say it's more sample efficient. Okay, however, this comes at the cost of higher computational requirements for LSTD. Okay, so what next? Next, we're gonna discuss deep neural networks as function approximators. With respect to your assignments, please be sure that you already submitted most of these. The value iteration, asynchronous value iteration, policy iteration, Monte Carlo control with and without important sampling, tabular Q-learning and SARSA, and now you can go ahead and start implementing Q-learning with approximation. Quizzes you have available, or hopefully you've finished most of these, the Monte Carlo control quiz, TD learning quiz, and step bootstrapping quiz, and now you have the value approximation quiz. And with respect to the project proposal, this is the wrong date, please be sure to submit the project proposal, to complete it and submit it through Canvas on time. Thank you.